And we need to start with 10.8. So what you guys all need to do, yeah, Maribel, we'll get to that. That's 11.2 though. But definitely, hold on. We need to go over what's due and what's coming due and all of that stuff. So let me, I went too far. Oh, and I haven't shared screen, have I? Have I shared screen? No, I have not. All right, so you guys can't even see what I'm doing. That's not good. All right, so there we go. So there's that. And then, okay, so today is 10, well, it's actually technically 11.2 and 11.3. However, I am very unhappy with some of your 10.8s. So we need to talk about 10.8 a little bit more, because you guys, literally not a single person got question 7 right. And that's a travesty, because question 7 was Hopital's rule, which you've already taken a test over. So we are going to go over that one, because some of you are trying to avoid the algebra and you can't. There's a reason you had to have a whole page to do that problem. So you need to pull out your 10.8 if you have not already, and you also need to pull out some blank paper, because there was just algebra mistake after algebra mistake as I was grading those last night, and those should not be happening anymore. You guys are Calc 2 students, so you need to pick it up a little bit on the algebra front. That said, you wouldn't be the first ones. I'm going to tell you right honestly, algebra, it is literally the first conversation I ever had with my husband when we literally just met each other as TAs at Michigan State. And we were like, what is it with algebra and calculus students? How come the calculus students cannot do the algebra right? So that was 1995, and it is still going on. So you are in good company. Every calculus student struggles with the algebra. So we'll go over that, and then we'll do 11.2 and 11.3. And I already have at least one, my math lab question from 11.2, although technically it's a pre-calc question. I actually found it in the pre-calc textbook. If you still have your pre-calc textbook, it's on page 209. There's a pre-calc book. So we'll go over how to do that as well, and then also talk about some other stuff from 11.2 and 11.3, because you guys are taking a test on all of this on Monday. So you have 5 days to get your shit together. Sorry to say, right? So we got a lot to cover and a lot of ground to cover. So let me see if I'm even recording. Let's see if I can, because I know Lindsay's always the one that's good about reminding me. Yep, I am recording. Woohoo! It's a miracle. I remembered for once. All right. So let's start with 10.8 number 3 for just a second. So everybody pull out your 10.8, pull it out, grab it. Grab 10.8, grab a blank piece of paper if you filled this page. I saw almost nobody get this correct. And this is not hard. So, and you need to know how to do it because it's all over 11.3, right? Ratio test, because that's what you're using for this. So we need to go over the ratio test a little bit more and the algebra involved. All right, so if you want to do the ratio test, which you do because there's a factorial in the damn thing, then you're going to want the limit as k goes to infinity of a sub k plus 1 over a sub k. This is the part everybody was good about. They were like, all right, that's the limit as k goes to infinity. Ooh, this is 10.8, number 3. Grab a sheet of paper. I'm not kidding. Almost every one of you got this wrong. So grab some paper. All right, so then it should be k plus 1 to the 40 over k plus, okay, and then I think it was Emma very wisely contacted me and said, hey, if the series is k to the 40 over k plus 3 factorial, she said, isn't k plus 1 plus 3 k plus 4? And I said, yes, Emma. Very smart. So very wise. She was texting me. Yes, 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 yes. So that's that. And then you're dividing it by, well, so I'm just going to multiply and kill all the middleman here. So it's k plus 3 factorial over k to the 40. Okay, most of you had that correct. We're doing good, right? So then where you messed up was the algebra. Okay, so this, let me just, okay. How do I put this? You don't have to rearrange it. You just have to do it correctly, right? And a couple of you completely lost sight of what this is. So k plus 4 factorial is, actually, let me write it this way. It's k plus 4, oops, I lost somebody. K plus 3, k plus 2, and so on, right? That's what that is. And a few people just went from k plus 4 to k. And I'm like, no, it works its way down. So you start with k plus 4, then k plus 3, then k plus 2, k plus 1, k, and so on, right? And then this guy over here is k plus 3 factorial. So it's k plus 3, k plus 2, k plus 1, right? K plus 1, right? So there's those ones. So that would be this guy and this guy. I just rewrote them there. Okay. And then you multiply by, okay, so this is k plus 1 to the 40 over k to the 40. Okay. Get it? K? Oh, that was funny. All right. You cannot make this 1. Several of you did that. You can't do it at this stage. It is 1. I totes agree with you, it's 1. But you can't do it inside the limit. You have to wait and do it later. So either you do your limits or you don't, right? You either pull the limits for both pieces of this simultaneously or you don't. You can't do halvesies. So you can't find the limit of one piece of it and say, oh, that's 1, and not find the other piece. That's not good, right? So, and while I'm on the subject, just for the record, this part here, cancel, right? All cancels. All right, so this is really the limit as k goes to infinity of 1 over k plus 4 times, this is k plus 1 over k all to the 40. Right, because of pre-algebra rule of exponents, right? If you have a to the b over c to the b, oops, somebody's back. We have a over c to the b, right? So because of that, we can put this together. Right? If you have two bases but the same power and they're divided, then you can take a divided by c, right? Okay, you cannot say 1. I know it's 1. I totally agree with you. But you cannot just say 1 here and times 1 over k plus 4. You either do the limit or you don't. But you don't do half of it. It's like being half pregnant. Right? Now, if you want to separate the limit, that's fine. If you want to write limit of this one times limit of this one and then say that that's 1, that's okay. But that's not what you were doing. I know I'm looking at your names, and I know a few of you just put a 1 right there when you still hadn't done the limit. You cannot do that. That is wrong. Okay, so then now finally you can let this go to infinity. Well, you can do this. So you can say limit as k goes to infinity of 1 over k plus 4 times 1 plus 1 over k to the 40. So that's really what you're doing. This will become 0, right? And this will become 0. So it'll be, or this will be 1 plus 0, right? So this will go to, now finally you're doing the limit. So you're letting k go to infinity. This becomes 1 over infinity, which is 0, times, and then this is 1 plus 0 to the 40, right? So that's really 0 times 1, which is 0. Okay. Now, several of you got 0, which is good. At least you knew where you were heading. But you were avoiding the math along the way, right? And that's not good. All right, so did everybody write that one down? That was the easier one, and honestly, a lot of you were a lot closer on that one, right? So you mostly had it right-ish, right? Which is good. But you were messing up your limits, right? You either take your limit or you don't, but you can't half-ass it. Okay, everybody wrote it all down, fixed your worksheet, figured out what you made a mistake about, because we need to do number 7 in a big old way, because literally none of you got it correct. Nobody in the whole class. So actually that's not true. Somebody in the class got it right, but it's not here. So, all right. Thumbs up me when you're ready, because I need to erase this before I can move to 7. So let me know when you're done writing. Thank you, I appreciate it. I'm waiting for Connor, CJ, and Martin. It's okay, take your time, just write. We'll wait for you. I don't want to leave you behind. All right, we're good. All right, let's talk about 7. Oh, you guys cracked me up. 7, there was a reason I gave you an entire page. This is going to take an entire page. Okay, when I do that, there's usually a reason, and avoiding the math involved didn't really help. So a lot of you lost a lot of points on this. All right, so the series is 18 to the k, k factorial over k to the k. So the factorial is like, hello, ratio test. Even though I didn't say it, there's no freaking way you're going to do this without a ratio test. So the ratio test says that r is equal to the limit as k goes to infinity of a sub k plus 1 over a sub k. Oh, by the way, if you filled your paper, mostly either erase it and start following me now, or grab another sheet of paper, right? This is going to take some work. All right, so, oh, and the absolute value. All right, so then this is the limit as k goes to infinity of 18 to the k plus 1 times k plus 1 factorial over k plus 1 quantity to the k plus 1. All right, are we all cool if I skip, hopefully, the middleman? Technically, it's divided by this guy, but if it's divided by a fraction, I can just flip and multiply. So I'm going to do k to the k over 18 to the k, k factorial. Okay, and usually everybody was good here, right? Everybody had that good first step, and we were doing all right. And then you guys usually got to the next bit. This was also pretty good. So right here, you were doing fine. 18 to the k plus 1 gives you an 18. And it's constant, so you can just pull the thing out, right? So you can have an 18 out in front. And then limit k goes to infinity. And I'm going to rearrange this. I don't have Amna here today. She was the queen of rearranging, and she was right. So let me just rewrite this. This is k plus 1 factorial over k factorial times k to the k over k plus 1 to the k plus 1. And I'll tell you right now, where you guys are making the mistakes is over here, right? This is pretty easy, although there were some mistakes here, but this part is the part that people are losing sight of what they're doing. So hold that thought. All right, so this is 18 limit k plus, or k goes to infinity of, and then everybody was pretty good about this. They recognized that, like, oh, this one's k times k minus 1 times k minus 2, da 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 da, and then this is k plus 1 times k minus 1, da 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 da. And so what's going to happen is everything's going to cancel and leave you just a k plus 1. So you're going to have a k plus 1 just sitting up there. I mean, over 1 if you want to write it that way. Okay. Times, you can't avoid the mess that this is going to make. So this is k to the k over. Now, I would like it if it was a k power, because if it was a k power, I can do what I just did on the previous problem and make it one fraction, right? So k plus 1 to the k plus 1 is really k plus 1 times k plus 1 to the k, isn't it? All right, because there's a 1, there's k, and k plus 1 makes k plus 1. See it? Why did I do that? Well, because then this k plus 1 cancels. And you are now left with 18 times the limit as k goes to infinity of k over k plus 1 all to the k power. And that is usually about where you guys got. Right? One way or another, people got here. So if you're sitting there going, well, I did that and it was fine. Yes, you're not done. You're only about halfway done. Because that, if you kind of think in your mind, oh, that's 1 to the infinity. I need to take the log of both sides. Looking at you, almost none of you did that. You can't avoid the algebra just because it's inconvenient for you, right? Just because you don't feel like doing it, right? If it's 1 to the infinity power, you learned in 4.7, you have to take the log of both sides. There's no other way to do this, right? So, and you can't get out of it. And a lot of you, matter of fact, all of you had the wrong answer. none of you got the right number because you're not doing the right thing, which you were taught in 4-7 is to take the logarithm. When it's 1 to the infinity power, take the log, bring the power down. You have to do that, right? All right. I'm off my soapbox. All right, so the natural log of r is equal to 18, the limit as k goes to infinity. I took the natural log, so I'm going to bring k down in front. So it's the natural log of k over k plus 1. I'm not really worried about the absolute values anymore because k over k plus 1 will always be positive, so I can just drop them. They're not needed anymore. They weren't really needed up here. I could have dropped them actually a while ago, but it's fine. All right, so then what is that form? That's infinity, and that's the natural log of 1. And I know from Algebra 2 class that the natural log of 1 is 0. So we have now turned it into an infinity times 0. That's why you're taking the logarithm. You still cannot apply L'Hopital's rule because L'Hopital's rule would require 0 over 0 or infinity over infinity. You have to do all of this. These are not things you can avoid just because you don't feel like it. Especially when it's something you learned before, especially when it's a problem similar to one that I did in class yesterday or Monday. All right, so this is 18. You now need to use the trick that we used in L'Hopital's rule section, which is to take that k and write it like this. And I feel like I'm going crazy, but I think I did one like this. In 10-7? Yeah, 10-7, 5b. I did it in class on Monday. It looked like this. None of you should have gotten this wrong. None of you, because I did one just like it. This is going to take the quotient rule and the chain rule. This is going to, literally, it looks exactly like this. Go ahead, 10-7, 5b. You have it. All right. So this is 18, limit. K goes to infinity. We are now using L'Hopital's rule. Yay, because this is now finally 0 over 0. So that would be, let's see, the natural log derivative is 1 over. So that would be k plus 1 over k times the derivative of that part, which is going to require quotient rule. So that's k plus 1 minus k over k plus 1 squared. And then it's multiplied by 1, negative 1 over k squared. Allow me. The one I did was the root test in 10-7. See that? We did that in class. Do you see it? See that derivative? See it? It's the same problem, but you had to get there. Yeah? Okay. So then, now I can cancel crap. So this is k and this is minus k. This is a k plus 1 and that's a k plus 1 squared, so that can go. So rearranging, this is 18, limit as k goes to infinity. All right, so I have a 1 divided by a k times a k plus 1, and then I'm dividing that by a negative 1 over k squared. Okay, so that's 18, limit as k goes to infinity of, oh, and there's a negative, yeah. So that's 1 over k times k plus 1 times negative k squared over 1. The k will cancel with that. The 18 will come out. So it's negative 18, limit k goes to infinity of k over k plus 1. Because I pulled that negative out in front because it's a constant, so it just kind of come there. And now, finally, you can use the table trick, which several of you said along the way. You're like, oh, table, it's 1. No, 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 no. It isn't 1. It's negative 18. So, and it's not even the answer. So this is negative 18. This is 1 by L'Hopital's rule. This is not the answer. It's the natural log of your answer. Right? So that means that r is e to the negative 18, which is, hold on, I'll find you guys your table. Ah! Oh, table. Let me go to the ratio test. E to the negative 18 is less than 1, right? Because it's 1 over e to the 18. So therefore, this converges. It's not 0, it's not 1, it's not positive 18. That is the correct answer. Write it down. And if you're thinking, oh, would I be required to do this on a test? Oh, hell yes, you'd be required to do this on a test, for sure. For sure. Right? This is something we learned on the last test. It was on the last sample exam and the last exam and section 4.7, and then it's in 10.7, and then it's in 10.8, which also means it's going to be 11.2 and 11.3 because ratio tests are all over 11.2 and 11.3. So write it down. Yes. Fix your errors. Now I realize I touched it with paper, so now it's a mess. Ugh, that's the problem with ink. But hopefully you can still make sense of it. Or hopefully you were writing down as we went, which would be very wise. Yeah. Everybody got it all fixed? Now, having done 11.2 and 11.3, which you should have all started long before you came to class today, right? As in like an hour or two before. No, as you should have started last night. So when you started your 11.2 and 11.3 worksheets, because of course you would never come to class not having attempted problems, if that's the case, you'll know, oh, I need to do this all the time because this stuff shows up in 11.2 and 11.3. Yes, it does. The ratio test is just one little piece of the larger thing that we're doing in 11.2 and 11.3, which is why 11.2 and 11.3 problems often take 2 pieces of paper, right? They take a lot of space. All right. Did everybody write it all down? Yes. Fix your mistakes. At least you guys know you're in good company. At least you know, like, hey, we all didn't do it. So only one student in the whole class got it correct, which is not good because this is stuff you guys should know, especially since I actually already did this derivative part for an earlier problem. Yes, Maribel?
Why would you not take the natural log of the 18?
18 is a constant, right? So it doesn't really matter, right? Here, hold on. Hold that thought. Let me go back. You've already pulled it out of the limit, right? So when you're taking the log, you're taking the log of the limit part. You're trying to take the log of this part, not the part that's the 18, that's the constant. In other words, you've already pulled it out. It's already kind of out in front. It's the limit part that you have to fight, the 1 to the infinity part. That's the part you're taking the logarithm of, if that makes any kind of sense. Fun with L'Hopital's rule. Yep. All right, we're going to get more, but I have, if we're good with 10.8, right, we should be good. So those 2 were the 2 that people really messed up. 4A, by the way, you should have done alternating series test, which several of you did. That's why I'm not going over it, because a lot of you got it and did just fine with it. But those of you that did not, 4A was alternating series test. And if you're going to do, one other thing before I go away from 10.8. If you're going to say you're going to do the limit comparison, you actually have to do a limit comparison. So a lot of you are like, so it seems so like it's similar to this function, which is convergent. Okay, fine. That it seems like it. You actually have to do it, and you'll see it when I wrote on a lot of your worksheets. Like you have to do the limit comparison. Like you have to take a limit of 1 divided by the other. So a lot of you figured out, like, I'm trying to remember which one it was. There were a couple of them, but you were like, oh, it's similar. It seems similar to this. I think it was 5A actually. And you were like, oh, it seems similar to 1 over k to the 3/2, which is true, but you have to do it. Right? So there's work involved. Like you have to find the limit of this thing divided by that thing, and you have to take the limit and do all the algebra and do all of that stuff. Maybe that one doesn't require L'Hopital's rule. So, but you have to do it, right? It's not enough just to say it seems similar to 1 over k to the 3/2. Sure. But unless you make a comparison, you have to do it. And a lot of you try to do a direct comparison. It's not going to work because there's a minus and a plus, right? So you can't do the direct comparison that way. This was a limit comparison. So you need to actually do the limit comparison to 1 over k to the 3/2. So direct comparison would be a lot harder to prove. I mean, you could do it, but you'd have to prove that this is somehow always greater or less than that new function, right? And since there's both a minus and a plus, that's a little bit harder to prove. It's easier just to do limit comparison. Okay, so 5a, for those of you, a lot of you were like, it's similar to this, so therefore must converge. It does converge, but that doesn't prove it. Like, you got to prove it. You got to do the work, right? There should be like a whole half page worth of work right there for that one. 5b required no work at all. 5a requires some work, right? You should do it. So just a little FYI, several of you fell into that trap. But it was good that you kind of recognized what it was similar to, so that was good. But you actually have to do it, right? A limit comparison test requires a limit. You actually have to find a big old limit and do it. All right, so that's 10.8. I've said enough about that. 11.2, I already have one question on 11.2. So let me erase first. Okay, so to find the radius of convergence, because you're doing this ratio test, you need to be able to do pre-calculus. So when I look at the pre-calculus textbook from section 3.5, those of you that had, this is for those of you that had pre-calc here. I don't know where it would be in your pre-calc textbooks, but every pre-calc textbook has these questions. You're looking at absolute value inequalities right here, like these guys. Okay, so I'm going to do one like this because there's a My Math Lab question that's similar to this, so it'll be the same kind of idea. And the reason you want it is because, of course, for the radius of convergence, you need your ratio test to end up being less than 1, right, when you do it. Here, you need this to be the case, right? So what happens in chapter 11 is you end up with a linear term here, and you need that to be less than 1, right? Something that involves x, right? Because the power series have a variable involved, right? Chapter 10 is all numbers and k's or n's, and that's it. But chapter 11 puts variables into it, right? And makes it into something else. And so you'll need to be able to solve a pre-calc problem like these, right? In particular, you want, they're usually less than inequalities because for convergence, you need it to be less than 1. So it'll work like this. All right, so I'm going to grab this one right here, although I could have grabbed, it doesn't really matter which one I grab. So I'll grab 3x plus 4 is less than 13. So grab a sheet of paper. Take notes. So we'll do a little pre-calc review. And this is of linear, so if you want to look it up online, if you want to go see like a Khan Academy video or something, what they are is they're absolute inequalities, absolute value inequalities is what you're trying to solve. Technically, they're absolute value linear inequalities because they'll always be lines, but if you just look up absolute value inequalities, you'll find it. So if you want to go watch videos on pre-calc, I ran out of space on my board. I should have started writing over here. It happens. It's okay. All right, so let me write this one down. All right, so 3x plus 4 is less than 13. So grab a sheet of paper, write it down because it'll help you. Yes. Hopefully you have paper. Hopefully. All right. So the way these work, you can do them a couple ways, but the easiest way is to turn it into a double inequality. So you make this turn into negative 13, which is less than 3x plus 4, which is less than 13. Right? Because if the absolute value is less than, I mean, think about what this is saying. If you look at your number line, right? Here's negative 13, here's positive 13, and your inequality is somewhere in between the two. Right? Its distance from the origin is less than 13. Okay, so then what you do is you subtract 4, but when you do it to all 3 parts at the same time. So you minus 4 here, minus 4 here, and minus 4 here. You're essentially doing 2 equations at the same time because it's convenient. All right, so this is negative 17 is less than 3x, which is less than 9. And then you divide by 3 to all 3 parts. Just like we subtracted 4 from all 3 parts, you'll divide by 3 from all 3 parts. So then you'll get negative 17 thirds is less than x, which is less than 3. Now, in chapter 11, you actually have to check your endpoints. So then we have the whole check endpoints thing. That won't mean anything to you right this second, right? Because this doesn't have any, there's no series attached to this, so I don't have to worry about it. But what you'll have to do is you'll have to check x equals 3. You'll have to check x equals negative 17 over 3. You have to check both of them back in the series to see what kind of series you get. Do you get a convergent series or divergent series? Because if it diverges, you leave it as a less than. But if it converges, let me just pretend. So if it converges here, then this would turn that into a this for your interval of convergence. You should have seen these because they should be in the notes. Now I'm curious. I should have them in there. Oh, let's see here. Yeah, it might be slightly simpler ones, but oh no, I got one in here that's interval of convergence, check endpoints. Yeah, I did one. It's right here. So I did one right in example 1. Right there. So we had a 4x minus 8 absolute value is less than 1, and so that's how you solve it. I did it right here. Negative 1 is less than 2 times that, which is less than 1. The same idea, right? So, and you add 16, and then you divide it by 8, and you get these two numbers. Could that be the interval? You have to check your endpoints. You have to go put those points into the problem, right? That's why these problems take 2 pages. They take forever, some of them. So that's one of the reasons why your test on Monday is another blank paper one, right? I'll send out the exam, which has no paper at all, and you will use a page per problem, at least. Waste some trees, go recycle it later, but you will use a page per problem, and some of them might take 2 pages if they're chapter 11. It happens. All right, so is everybody seeing how to do those pre-calc things now with the absolute value inequalities? Seeing them better? Yes, better. Good. Are we good on pre-calc? It's okay. You know what? It's probably this thing in pre-calc. Well, one, maybe your teacher didn't teach it. But it's this thing in pre-calc that kind of like washed over. You're like, okay, it's no problem. And then you didn't realize how you needed it. And now 2 classes later, you really need it. Like, you got to be able to do it. Like, because we got other things to do. So that might be an issue. And I was really excited to pull up my husband's pre-calc book because I don't get to pull it out very often. It comes from a shelf behind me. And I was like, ooh, I get to pull out a pre-calc text. All right. Because I don't teach pre-calc very often. Not that I can't. I just don't. I have other things to do. All right. So better on that one. Oops. Oh, sorry. I'm missing the chat. Sorry. I forgot about that one. Hold on. Let me pull that chat over. Okay, so is that better? That should help. There was a My Math Lab question in 11.2 that worked like that. That's like that same basic idea. So are we all good? I'll leave it up for a second. And I do see some questions coming in for 11.2. But there was a My Math Lab one. So this was a My Math Lab question from somebody. Everybody good? You wrote it all down? It's not bad once, you know, actually, now that you see it, you're probably like, oh yeah, pre-calc, this isn't so bad. This is good. I can do this. So it just takes a while to kind of think about what you're doing. All right, so if we're good there, I see 11.2, number 8. Okay. I'm waiting. Everybody good with this one? Can I erase it? Anybody got questions on it? Or need to see another one? Good. Thumbs up in me. Mirabelle, Emma, Jessica, you guys okay? Everybody see how to do that one now? All right, we're good. All right, so I'm erasing now. I need a board. You guys hopefully have a whiteboard. Have you bought one yet? I know Daniel's got one, and I think I remember Mirabelle having one during the exam. That's not a bad idea on the test to have a whiteboard for yourself, just to kind of be able to knock out ideas, right? My recommendation to you for 11.2, number 8, is to remember that we have a list that might be helpful. So we have a list of, what do you call it? These ones, Taylor series, Maclaurin series, could be helpful. I also think this particular one, I thought I did one like this in the notes. Yeah. So number 8 is like, it's like number 6 in the notes. Also a little bit like number 7. But it's like 6B actually, right? So it's integration. So remember, if you have your power series, you can use it to find new series, right? So what they're saying for number 8, if I were you, I'd grab paper. I mean, yes, you're going to get an answer. It's your multiple choice answer, but you need to know how to do this. You have to take a test on this, and it won't be multiple choice in 5 days. 5 days from now, you'll be taking a test on this. All right, so grab some paper. Hopefully, that should have been my theme of the day. I should have said to everybody before class, you're going to need paper. grab some extra paper. All right, so let's see here. So we have a series that is 1 over x equal, or 1 over 1 minus x, excuse me, equals 1 plus x squared plus blah, 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 blah. All right, so let me write that out. Okay. So 1 over 1 minus x is equal to, let's see, 1 plus x squared plus x cubed plus blah, 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 for the absolute value of x is less than 1, right? Because that's your interval of convergence. Okay, so they want you to use this series to come up with a series for the natural log of 1 minus x. So what they want is they want a power series. Now you guys get why we didn't call them P series earlier. Or it's me, why we did call them P series, the ones that we were working with in chapter 10, because these are power series. All right, so power series are a different thing. So I want a power series for the natural log of 1 minus x. Like, that's my goal. Good so far? So natural log of 1 minus x. Okay, so then let's see here. What do they want? We can integrate it. So the thing about getting to natural log of 1 minus x would be if I integrate both sides with respect to x, like that, right? And then, hold on. Yeah, I can't help but wonder if this is a typo. Now that I'm looking at it, Lindsay, I almost wonder if it's negative natural log of 1 minus x. I'm positive that it is, because there should be you'll see it. There's going to be a negative here when I do this, because when I take the integral of this side, the integral of 1 minus x, 1 over 1 minus x, excuse me, is the natural log of 1 minus x. But then you have to compensate for the fact that it was a minus in front of that, so it would actually be a negative. I think that's a typo, looking at it. It's just my gut reaction. I think it should be negative natural log right here. I'm almost positive, but I'll double check in a second. But I'm almost positive that should be a negative natural log of 1 minus x. For another hint, if you're looking, just so you know, it's in the table. This is why I know I think I'm right. Right? See it? It's right there. See? So I'm almost positive that there should be a negative in front of that. Sorry about that. I got it from the author, so it's possible they have a typo. All right, so, and that is equal to, and then we want to integrate every single piece of this. So the integral of 1 with respect to x is x. The integral of x with respect to x is 1/2 x squared plus 1/3 x cubed plus 1/4 x to the 4th plus blah, 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 which is a. But I think it's a typo. I think there should be a negative right there. So if that's the question you were having, Lindsay, I agree with you. We should make a note. You know what? I'll send everybody a remind. I'll see if I can manage it right now. Oh, we'll see if I can do this. So, oh my God, I'm on the computer. So, hold on. Come here, Zoom, go away. All right, so let me message everybody. It's not liking me because I'm on the internet, because I'm on Zoom. Let me make a note. Maybe I can send it on my phone. Maybe that'll be easier. Oh, now I've lost the gallery. Oh, there you guys are. All right, so I'll send everybody a little remind and just say, hey, note, it should be negative natural log on number 8. Okay, it's not gonna let me do it. Apparently my phone also won't let me write into text. This is terrible. All right, technology and you. All right, so here we go, I got it. Okay, so send announcement to Math 154. Next, okay, so that way you guys all have it. 11.2, number 8 has a typo. It should be negative natural log. Oh, I hate doing math on my phone because I have to constantly go to that other menu. All right, there you go. Okay. Hopefully I sent it right. Yeah, I did. All right, good. Cool. All right, so there you go. So it's A. Sorry about that. There's a typo on that one. I have to fix it on the file, but I can't do it right now because of you guys. It's not your fault. It's just because if I try to open up one more window, then Zoom is going to freak out on me. All right, so that's that's 8. And then 13. Is there anything else, by the way, in the first couple of pages? Any more typos I need to know about? I'm going to fix it right now on my paper so that way I know. And then I'm going to fix it right here. But I can't fix the file yet. Anything else on the first 2? You can use the table to your advantage. This is going to be given, you get to use this on the test. However, sometimes one of the things I'm having you do is prove those. So for example, like proving that this leads to that or something like that, right? So you can't be like, it says it in the table. If I am asking you to do it by hand, that means you actually have to take the derivative or take the integral to generate the other one. Just a little FYI. But it's nice to have the table because at least then you know where you should be going, right? It's like, oh, that's where it should be heading to. That's good to know. All right, so that was 11.2, number 8. All right, I see 11.2, number 13. All right. 13, here you are. Okay, so is it, my numbering's a little off, so let me see if this is right. Sorry, I'm looking for my thing. It's this one, right? With the 1 over 1 plus 1 over k to the k squared x to the k, that one? That's 13, right? Okay, so my recommendation is use the root test on this one. The reason I'd use the root test, 1, there's no factorial in it, so I don't have to worry about, ratio tests. But 2, because of those powers, because that's power k and that's k power, like both of those are k powers. If I take the kth root, it'll make things easier. Does that make sense? Okay, so let me write it down. So I would do the root test because it's asking you, it wants you to find the radius of convergence, right? So that's either ratio test or root test. The interval of convergence, I've used this page so much, it's ripping. The interval of convergence for the ratio test or the root test, they both have to be less than 1, right? So either one of these will come up with an interval of convergence for you. We don't use the root test as often, but for this one, it's the way to go, right? The root test. Oh, sorry, I clicked on that. Okay, so if I look at my series was 1 plus 1 over k to the k squared x to the k. Okay, so then I want to use the root test. And so it would be the limit as k goes to infinity of the kth root of the absolute value of 1 plus 1 over k to the k squared times x to the k. And it has to be less than 1, right? That's my goal, is to get this sucker to be less than 1. So this is rho, if you will. So I need rho to be less than 1. Good so far, right? All right, so hopefully the root test is making sense to everybody. Like, oh yeah, powers. There's a lot of powers in there, so maybe k powers. So maybe taking the kth root will make things go easier. Cool. Okay, so let me rewrite this. This is the kth root of. So this is the limit as k goes to infinity of And then this is 1 plus 1 over k to the k squared divided by k. So that would be 1 plus, oh, yeah, let me write it this way. 1 plus 1 over k to the k, right? Because k squared divided by k would be k. And then absolute value of x, right? It's to the k over k. Here, this is k squared over k. If you can, that's division. Sorry if that doesn't look right. Sorry. I'm trying to write it in such a way that you guys know what I'm doing. You see what I'm doing? I'm taking this k through out here, and then I'm putting it underneath. So this k right here becomes this k right here and this k right here. Good. Okay. Sorry, I can't stop myself. And okay, just never mind. We're good. All right, moving on because it's just too many k's today. All right, so this is the limit as k goes to infinity. I think my dog just jostled my microphone. Of 1 plus 1 over k to the k. And then this is the absolute value of x. You can't drop the absolute value. That's kind of what you're looking for, right? So you have to leave this in absolute value. So if you were wondering in chapter 10, why is it we have these absolute values all over the place in ratio test and root test? Because we drop them like first thing, we just make them go away. And the answer is it's not for chapter 10, it's for chapter 11. Chapter 11 is when it matters, right? So in chapter 10, yes, we drop the absolute values almost right away. I kind of forget sometimes, I just leave them in there for a while. But because k is positive, you never really have to worry about it in chapter 10. But in chapter 11, you have the included variable of x, and x can be anything. So you need absolute value around that x. I don't need it around the k part, right? If there's no x, that's a chapter 10 problem, right? Because that is something we know. We'll talk about that in a second. But this, right? We know that this is positive, right? K is positive, but we don't know what x is. X is a variable. X can be all sorts of things, okay? You know what I'm seeing? I'm seeing a 1 to the infinity. Yeah. However, this one is one that you should know off the top of your head. This is one that we learn and teach ourselves in Calc 1, as a matter of fact. But I don't know if you guys know that. So let me break this up. Let me do this. I can do it this way. So if I look at this form, maybe I should have given you guys more space on this. If you don't know it off the top of your head, because you should, but if you don't, that's okay. This is, hey, a 1 to the infinity. Logarithm time. Yep. So, and honestly, we only really care about that part. I'm gonna leave the x out of it for right now, and I'm gonna go figure out what this is. So just bear with me here. If I have L equal to the limit as k goes to infinity of 1 plus 1 over k to the k, I'm just gonna go figure out this part on its own. For those of you that don't know what it is off the top of your head. So then you take the log of both sides, and when you see it, you'll get it too. You'll realize, but that's okay if you don't get it. So I'll worry about this because what I'm going to do is I'm going to go put it in. So natural log of L, I'll bring the k down. So this is net limit k goes to infinity, k times the natural log of 1 plus 1 over k. Oh, that's looking familiar. Matter of fact, I'm going to rewrite that sucker. This is k plus 1 over k, right? Because if I multiply that one by k over k, so this is the limit as k goes to infinity of the natural log of k plus 1 over k divided by 1 over k. It's the same one we did earlier. L'Hopital's rule, because now it's finally 0 over 0. So L'Hopital's rule, I would take the limit as k goes to infinity of negative 1 over k squared. And then this would be k over k plus 1 times the derivative of that would be k squared. Then I have a k times a 1 minus a k plus 1. Like that. So I think I'm doing that right. Yeah. So the derivative of this would be 1 over that. Yep. Yep, I am. So then this is the limit as k goes to infinity of the k's cancel. You're left with k over k plus 1, wait for it, times negative 1 over k squared all over negative 1 over k squared. And these two bad boys cancel. And you're left with the limit as k goes to infinity of that, which we know by L'Hopital's rule, as well as the lovely table that we have, the magical polynomial over polynomial table, that this is 1. So the natural log of L is 1. So therefore L, which is what I'm trying to find right here, I'm trying to find that number. Oops, sorry, you can't see that. I'm trying to find this. This part right here is going to be my L. Using all of this L'Hopital's rule action, I know that L is e to the 1, which is e. So the reason I was saying you guys should all know it is because that's the definition of E that you learn in Calc 1. As a matter of fact, your teachers probably got their panties all in a twist about it. Like, oh, this is the real definition of E. You're finally learning it. Oh. It's also, for the record, on your notes packet. It's just straight up given to you. It's right here in the special limit section for Calc 1 general reference. Because in Calc 1, you don't really have the tools at your disposal for being able to find these. But now you do, right? So the way to get that is the whole logarithm thing with the stuff, right? So you do all that work for the second time today. Yes. E. You can't avoid it just because you don't feel like it, right? Although in this case, you probably could. I would probably accept that that's E, because it is. It's E. But it's also, I mean, that is the definition of E. E is defined as the limit as k goes to infinity of this, which is why I was saying you guys should all kind of know that, because that should be how E was defined for you in Calc 1. So this is E times the absolute value of x. E is just a constant, right? Oh, limit. Sorry. Well, actually, no, there's no limit anymore. Sorry, because we took the limit part. The absolute value of x is out of it, right? We didn't need to drag it with us because there's no k in there anyway, right? So we just kind of went off to the side and figured this out because I didn't feel like slapping an absolute value of x on every piece of this. It doesn't make any difference, right? So this is the part that I needed to find that value, and I did, and it's E. Right. So then that means that the absolute value, see, absolute value inequality. So if you want the, do you want the interval of convergence or just the radius of convergence? I can't remember what we're doing here. As if you want the interval of convergence, you want the absolute value of x to be less than 1 over e. And that means negative 1 over e is less than x, which is less than 1 over e. That's the interval right there. I don't know if they asked for it. I can't find the problem anymore. So that's the interval of convergence. The radius, I mean, think about what that is. It's from negative 1 over e to 1 over e. The center is obviously 0 because that's symmetric, right? So the radius of convergence is the distance from the origin out to 1 over e. So that would be 1 over e. Sorry, that looks weird, but it's 1 over e. Hear what I'm saying, hopefully. So 1 over e is your radius. Did everybody catch that same technique that we showed on Monday and we showed today and we learned to do in chapter, whatever the heck it was, chapter 8, but it was 4-7. It was on the sample exam. And the one on sample exam was like tangent to the cotangent or something like that. And a lot of you tried to avoid getting out of having to do this. But you need it. You need that skill. So get used to it. I'm sorry to say. It's not gonna go away. So you're gonna have to get used to it. Well, I should say that it will go away because I think we don't use it in chapters 9 and 12, which is the last bit before the final. But you do need it for the test on Monday. Good, wrote it down. So if it asks for radius, it's 1 over e is your radius. If it asks for interval, it's from negative 1 over e to 1 over e. Or technically you can write the interval as the absolute value of x is less than 1 over e because that is the same thing as that. Is that better for 13? I can't find where 13 was, so I lost it in all my paper shuffling. We're good? Okay, we're good. I'm gonna put these notes away. Otherwise I'm gonna lose it. All right, so that one was 13. And then I saw another one in there, 17. All right. 17A and B, is that the deal, Shayna? Hold on. The 1-0. I feel like I didn't give you enough paper. That's my personal opinion. I think you should use a sheet of paper for each of these. I think I should give you more paper for this. I think I didn't want to because I thought 9 pages would just be a little too scary for you, but I think you should have another sheet of paper. Honestly, I think 15 and 16 should all have their own sheet of paper also, because I'm writing pretty small when I do these. So, all right, I'll do 17. Let's do it. 17, it makes sense because if 17, no wonder you're asking about it, because those are always the hardest ones. The ones that involve differentiation and integration are always going to be the most tricky, the least fun. Let's put it that way. All right. So let me shove that page aside. Everybody got it? Good. We good for whatever this one was? 13? 13? We're good? Did y'all write it down? Daniel, question? Or were you just trying to thumbs up me and hit your microphone instead? I know Shayna already thumbs up me. Jessica, Geza, you guys okay? Did you write it down? Yep, we're good. Okay. CJ, Connor, you guys okay? Mirabelle, you good? Don't want to leave you behind. We got more fun. Oh, 17 is just a beast. So yeah, it makes sense. 17 is differentiation. All right. So, okay. You have a power series. You're looking for g of x, which is equal to, okay, so let me just write this. I think take out more paper. I think you're going to need it. That's just my personal opinion. I think I'm going to need more than one board. Actually, no, I won't. I'll be able to do it. All right, so I want to find g of x, which is equal to 1 over 1 minus x cubed, given f of x, which is 1 over 1 minus x. Okay. 1 over 1 minus x is on my Taylor series, my power series expansion things. Hold on. I know you're in here. Where'd you go? There we go. Okay. 1 over 1 minus x is right there. See it? So we're going to use that series, and then we're going to develop the 1 over 1 minus x cubed. Okay, so, and it mentions right in the top in the instructions, it says power series, centered at 0, which means it's a Maclaurin series, by differentiating or integrating the power series, perhaps more than once. Okay, so let's think about this for a second. What would be the derivative of f of x? So f of x is equal, oh, geez, that was really loud. Sorry, you guys can't hear this, but maybe you can. I've got my, let me see if I can mute it. Outlook, like my school email, and it's constantly sending me updates and stuff, and they're super loud. It's really annoying. Maybe I'll just close it. Let me close, because that's annoying. Ugh, this is really blaring. Okay, so this guy right here is x to the k, according to the table. It's x to the k for absolute value of x is less than 1, which of course, if you remember, when I graph it on Desmos, that means that for that interval from -1 to 1, that graph is on top, right? That series graph is approximating this function, which is freaking amazing, right? That you can take a series, a discrete series, and have it map onto a continuous function. That's phenomenal. And it's very important for physics, engineering. You need to be able to do that. It will be in differential equations, I can guarantee. It's not going to be in Calc 3 so much, but it will be in other classes higher up for sure. Your upper level mechanics, your upper level stochastic modeling, all that good stuff. Okay, statics, things like that. So you will have Taylor series. Let me just put it this way: chapter 11.2 and 11.3. They're not going to go away. They're going to get worse, and they'll get worse in your physics classes, your engineering classes. That's where you're going to see these suckers again. right? And you will see them. Okay, so you'll see it in differential equations if nothing else. I know you will because I know who teaches it. It's my husband. All right, so, but you won't see it in Calc 3. So if you want a breather, you can take a breath. All right, so I want to take the derivative of this because I want to figure out how many times I have to do this to get that guy. Okay, so let me think. How am I going to do this? I'm just thinking about how I want to set this up. So if f of x is equal to 1 over, can I just rewrite this real quick? 1 over 1 minus x is the same thing as 1 minus x to the negative 1, right? And this bad boy right here is 1 minus x to the negative 3, which is kind of a clue of which way I need to go with this. And then this is equal to the series x to the k, okay? If I take the derivative, let me do that. F prime of x. That would mean that I bring the negative 1 down in front. So that'd be negative 1 times 1 minus x to the negative 2. And then I'd multiply by the derivative of the inside, which is a negative 1. Right? So that would be 1 minus x to the negative 2. Now that's equal to the derivative of this guy. But this guy must be equal to, you would take the derivative of it like you would take the derivative of anything. I mean, if it's x to the k, it would become k times x to the k minus 1. Okay, now here's the thing. When you start off your first series, they tell you right here that x is 0, or excuse me, k is 0. So going from 0 to infinity. When you do the shift, when you take the derivative, you now shifted it, so it no longer starts at 0. It now starts at 1. Like that. Good so far. You can see, oh, we're edging a little bit closer to what we want, right? So this is a little bit closer, but it's not there yet, but it's closer. So now I need to take the derivative of this. I need to take the second derivative. So second derivative, sorry, I should have given you more paper. I apologize. So the second derivative is you bring the negative 2, 1 minus x to the negative 3. Ooh, 1 minus x to the negative 3. That's looking good because that's what we want, right? But what we don't want is that stupid 2. We'll get rid of that in a second. And then we're multiplying by negative 1 because, of course, of chain rule. Right, we're taking the derivative, so we need to multiply by the derivative of the interior, and the derivative of the interior is negative 1. All right, and that's equal to, all right, so now I have a k, it's sitting there, but then I bring the power down, k minus 1, x to the k minus 2. I subtract 1 more from that power. But now I'm no longer starting at 1, I'm now starting at 2. Yeah. Okay, so then, let me think. This is super close. So if I rewrite this, this is 2 over 1 minus x to the 3 is equal to all that's jazz, right? Now, I don't particularly like that it's starting at 2. I want to shift it and make it start at 0. Starting at 0 would make me happy, right? So if I want to start it at 0, I have to do a shift. Okay, if I want to start at 0, what you're doing is you're adding to each of these. So it'll become k plus 2 here, k plus 1 here, x to the k. Take a moment and realize what I did, right? It'll work. Like put in a number in your head. What will it be? 2. 2 times 1, x to the 0. What will this be? 2 times 1, x to the 0. See? It works. I've shifted everything 2, right? I added 2. So instead of k, it becomes k plus 2. Instead of k minus 1, it's k plus 2 minus 1, which is k plus 1. Instead of k minus 2, it's k plus 2 minus 2, which becomes k. So that's how you can shift for the power series. So then this is really close, right? So g of x is 1 over 1 minus x cubed. It would be a half times this series. Good there. Okay, so we've got the series. That's one of the things they wanted, right? They want what this function is a power series, right? Derived from this other power series, which we did. So we took the original power series of 1 over 1 minus x, and we are slowly deriving by taking the derivative multiple times, right? That's why it says more than once in the instructions. So we had to take the derivative twice to get here. All right, now we need the interval of convergence. So we need the interval of convergence is this, because we still haven't messed with the x when we did this problem. Like that didn't change, so it's still x, or absolute value of x is less than 1. So that means that my interval of convergence is from -1 it's -1 is less than x, which is less than 1. Now the trick is, I don't know if it's less than or less than or equal to. Mm-hmm. Or if you want to write it another way, here. Mother, nah, I'll just leave it. Right? In interval notation. And I don't know, maybe one of these needs a bracket. I don't know. So I've got to try it. So I have to check my endpoints. Always, right? You always have to check endpoints all through chapter 11. So you go, okay, if x is equal to -1, look at my series, right? It'll become, let's see, it'll be 1/2 k equals 0 to infinity. It'll become k plus 2 times k plus 1 times -1 to the k. Well, divergence test, right? Look at that thing. There's no way in hell that's going to 0, right? Divergence test says, hey, if it's not going to 0, it diverges. You're done. That sucker diverges, right? There's no fraction in it. How is it going? Like put in like 100. It's going to be 102 times 101 times 1, right? So it's going to be big. It's going to infinity, right? So this is by divergence test. By divergence test, the sucker diverges. I guess I should say it this way. Right? This thing is not going to 0. Right? It's going to infinity, as a matter of fact. All right, if you take the limit of it. All right, so same thing with the other one, by the way. If x equals 1, you have 1/2. It's even worse, actually. It doesn't even alternate. It's just this. That goes to infinity. I don't know what to tell you. Like that, it's going to diverge, right? The only way it has a shot of converging is if the limit is 0. And even then, it's not guaranteed, right? That's the divergence test. The divergence test says, hey, if this sucker, if this sequence in here, remember that's a sequence, that's the part that makes it a series. But if the sequence doesn't go to 0, then you diverge and you're done, right? And that's true of both of these, right? So the limit as k goes to infinity of k plus 2, I could have written this up above, times k plus 1 is infinity. So it diverges. Right? It's again, it's the divergence test. This is the reason for both of them, right? So for both pieces. So that means that the interval of convergence, which was actually what was asked for, is right here. There's no equal to, there's no bracket. It is just -1 to 1, and that's it. There's not going to be a convergence on the endpoints on this particular one. Good for 17a? Sorry, I really did not give you enough paper. I know, I'm sorry. Shayna's good. What about the rest of you? Hopefully you were taking careful notes. Good. Because I got to erase it because that filled the whole board. And now I got to do it again. So 17b is also very tricky. I see you, CJ. Hold on for 12 and 18. I'm getting there. I tried to warn you guys. 11.2 and 11.3 are going to be pretty brutal. All right, so if we're good, let's go to 17b. 17b doesn't require derivatives. It's going to require integration. Sorry to say. Okay, so 17b. What are we doing? Okay, so we want to find g of x is equal to the natural log of 1 plus x squared using f of x, which is x over 1 plus x squared. Oops, sorry. There we go. Hold on. There's a dog moving underneath my legs. You done? She's large and she's shifting underneath the desk. She's right up there. She is. She's flapping around right beneath the table. All right, come on out. There you go. Okay, exciting. If you guys want to see her, she's right there. She's moving to a different bed in the room. All right, so I need 1 plus 1, or 1 over 1 plus x squared. So I need to do some work right there because I don't have 1 over 1 plus x squared just on the side. I have this one right here. And so that's what I'm going to use to kind of help myself a little bit. Okay, so we need to figure out this bad boy before we even like get anywhere. So let's look at f of x. So f of x is, I'll just do it this way. F of x equals x times 1 over 1 plus x squared. All right. Okay, so that's x times, and then this guy I've got a series for, because I can use that series from the table and say that this is the series from k equals 0 to infinity, -1 to the k. And now here's where the fun begins, because when you look at the table, it has just x, but we're going to use x squared. So what that means is it's going to be x squared, x to the 4th, x to the 6th. So instead of x to the k, it's going to be x squared to the k. Like that. Good. Okay, and then we're multiplying by another x. So that x here and that x here, they can combine, right? And it becomes, wait for it, this is the series from k equals 0 to infinity, -1 to the k, x to the 2k plus 1. And then again, that's for absolute value of x is less than 1. Oogly doogly. So there we have it. So I'm going to use that series right here. So this is my x over 1 plus x squared, and I'm going to use that to come up with my natural log. How? Okay, well, the derivative of natural log is 1 over. You seeing the track I'm laying down? Think about it. The derivative of this guy is that guy. So that means that if I want to find the g of x from f of x, I'm going to have to integrate. Okay, so let me take f of x and let me integrate it. Sorry, I'm just thinking here. Yeah, x over 1 plus x squared. And I want to integrate it with respect to x, which means I also want to integrate this guy over here. Well, yeah, all right, I'll do it. I'm just thinking about the order I want to take this in. All right, x to the 2k plus 1. Okay, so I want to integrate both of these with respect to x. Okay. Well, technically, to do the one on the left, we could use u substitution, right? Because u is that denominator. And therefore, du is 2x. So I really want 1/2 du. So I'm just going to do this part over here, and I'll come back for that. So give me a second. So this is equal to, this side over here is equal to the integral of 1 over u du times 1/2. Oh, 1 over u. And then I'm going to put the 1/2 up here. 1/2 du. Sorry if that's a little too close. Hold on. I don't want that to be so close. So I'm using all of that to inform that piece right there. Okay. So then the integral of 1 over is natural log. So this is going to be, and I'm just going to write it now, it's a half natural log absolute value of u, which is 1 plus x squared. And I don't really have to worry about the absolute value because x squared is always positive. So this doesn't do me any good. And that's g of x right there. See it? Hello, g of x. Hello there, old buddy, old pal. All right, that's the part I want. I'm going to multiply by 2, but I'll get there. Right, so that's the thing I'm looking for. Seeing it? Good. So I took the f of x they gave me and I integrated it and I got g of x. Well, a half g of x, but still, I got g of x. So now I have to integrate this side. Yeah. Okay, so to integrate over there means I would add to the power, right? So remember, if you're sitting there worrying about like the -1, the -1's not relevant, because what happens when you take an integral of the -1 doesn't have an x in it, so it's just going to be -1 to the k. It doesn't really do anything. What matters to you is this x to the 2k plus 1, right? Because when you integrate x to the 2k plus 1, it becomes x to the 2k plus 2, and you divide by that new power, like that. Oh, I've got my symbols. Sorry. There should be a summation notation here. Coolness. All good. Think. Technically, this is still from 0 to infinity. This one actually works out, so it doesn't lose terms. Derivatives lose terms as you go. It's one of the problems with derivatives, right? Because the derivative of a constant becomes 0 and it disappears, so it gets lost off the front end. That's not going to happen here with the integration, so we don't have to worry about that the way that we did for the other one. Okay, so yeah, so there's my lovely term. Isn't it gorgeous? And then I would multiply everything by 2, right? So I would take, so let me put it this way. I haven't really done anything. So this is k equals 0 to infinity, -1 to the k, to, or x to the 2k, my bad. And I'm going to do myself a favor and factor down there like that, because I know where I'm going with this. All right, so then when I multiply, right, because I got my g of x, I don't really need to get you guys confused there, but that's g of x right there. So I want to get this part by itself, so I'm going to multiply by 2 over 1 to both sides. So they cancel here, but it also cancels here. That's why I factored out the 2. And so therefore, the natural log of 1 plus x squared is equal to this series from k equals 0 to infinity, -1 to the k, x to the 2k plus 2 over k plus 1. And you're good. That's it. It's still for absolute value of x is less than 1. You're not done with the problem. You're done with finding the series. You found the power series. Right, there you go. So there's your power series right there. That's what one of the things they wanted. The other thing you have to do is any power series needs to be accompanied by an interval of convergence. So this is what you think the interval of convergence is. However, you have to check your endpoints. So, and you're not done unless you do. So you have to write. So sorry, I should have given you more paper. I apologize. So let's check endpoints. Okay. So if I put in x equals -1 into that lovely, lovely series that I generated, I would have -1 to the k, that hasn't changed, times a -1 to the 2k plus 2 over k plus 1. Okay, so that's -1 to the 2k plus another k makes k, right? I feel like I'm going crazy. 2k plus 1, or tk plus 2 plus another k. 2k plus 1k makes 3k. Yeah. So this is -1 to the 3k plus 2 over k plus 1. It's the alternating harmonic series. I mean, it's glorified, but that's what it is, right? So this is the alternating harmonic series. So it's going to converge, right? So alternating because of the top, harmonic because of the bottom. So it converges. Okay, and then if I put in x equals 1, I have negative 1 to the k, 1 to the 2k plus 2. Well, 1 to the anything is just gone. There's nothing there. Over k plus 1, which again is the alternating harmonic series. I mean, it alternates slightly differently, but it's still an alternating harmonic series. So therefore, it converges. And that means that my interval of convergence would be from negative 1 to 1, both of them with brackets, right? Because you're really saying you can equal negative 1 and converge, you can equal positive 1 and converge. Everybody good? Write it down. Those are the hardest ones, in my opinion. The ones that require derivatives and integrals are such a pain because you really got to, if you can't see the relationship, if you can't figure out how to get from the function that they gave you to the other function that they gave you, then you're stuck, right? You've got to basically take derivatives and take integrals until you figure out which way to go and then start going from there. Good. All right, so 12, 11, 2. Hold on, I got to go back for 12. You require me to find earlier pieces of paper, CJ. Not good. All right, so calculus is not all a lie. My husband just walked by. All right, so number 12. Let's see, we're doing the interval of convergence, radius of convergence. All right, so I'm going to have to erase. Did everybody write everything very carefully? Because you will have to do this on the test. It will take you a full sheet of paper. You must be neat. You must be organized. I must be able to follow your work. Thank you, Emma, for thumbs upping me. It's not easy. I'm not telling you it's easy. I'm telling you these are some of the hardest problems you do in this class because they're so technical. You have to really keep everything clear, organized, neat. And some of you are really good about neatness and some of you are not. And I'm sorry to say that can be a real struggle. So you've got to get your relationship figured out. You got to get your series figured out. Then you got to get your relationship figured out. Then you got to take your integral or your derivative. Then you got to come up with your new series. Then you got to come up with your new interval of convergence. You got to check your new endpoints. Blah. Right? It's a lot of work. All right. Are we good? So if you thumbs up me, I'm going to head to 12. Yes, we're good. Waiting for Connor and Jessica and CJ and Daniel. You guys good? Okay. All right. So we're good. All right. I see it. Let's do 12. Stuff is not easy. I'm not telling you it is. You're not hearing me say it. But I'm also telling you, the sad thing is that, you know, it's not easy. And this is some of the stuff you're actually going to use again. I know. It's kind of heartbreaking. All right, so 12. Let's do 12a. All right, so 12a starts with x minus x cubed over 4 plus x to the 5th over 9 minus x to the 7th over 16. And plus da, 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 da. Okay, so we're supposed to come up with an interval of convergence. Before we come up with an interval of convergence, we kind of need to have a series. Like, I mean, if you're going to do the ratio test, which is what you're going to do, I mean, if you're going to do that, you need to have the series figured out. So this is the part that will be your audience participation point for the day, right? So can you figure it out? So remember, this would be, I mean, it's up to you, but I'd probably start at 1. So this is k equals 1, this is k equals 2, this is k equals 3, this is k equals 4. You've got to figure out that pattern as a series. Otherwise, you're dead in the water. Okay, I'll give you a hint. It involves a fraction. I'm waiting. You can just do part of it. Do the denominator. What's the denominator going to be? Oh, Ben wrote it all down. Yeah, interesting. You did k plus 1 squared. Oh, you started at 0. That's why. Yeah, it's actually a little harder to start at 0 on this one. If you start at 1, I'll write yours down too also, Ben. It's k squared. If you start at 0, sorry, I was unhappy with my other marker, but this one's a little thicker. Then everybody see what he's doing? It's k plus 1 squared. They'll both work. So either one's correct. I'm not telling you you're wrong or anything. All right, and then you've got the -1 to the k. I would have -1. Okay, so if you look at Ben's here, everybody see, he wrote that because you need to have some component like that to alternate. So at his first term, when you put 0 and -1 to the 0 is +1, and that's why his first term is positive. For me, because my first term is 1, I'm going to need -1 to the k plus 1, like that. That way it'll turn even for the first term, but odd for the next term, but even for the third term and odd for the fourth term. So either one will work. Okay. And then x. It's obviously x to the something. For me, it's 1, 3, 5, 7. Those are odd numbers. So it'll be 2k minus 1. Because Ben is starting at 0, it's 2k plus 1 for him. So check over both of those series. They both work. It's kind of whichever one you feel like, right? Because it's not going to change anything. You're still going to have to do the ratio test either way. So it doesn't really make any difference. Everybody seeing it? They are different though, right? So it matters where you start. If you start at 1, it has to be this one. If you start at 0, it has to be this one. They're related to each other, but they're not the same. You could also do k minus 1 on that one. It doesn't actually matter. Like it just needs to be alternating. So k minus 1 would be a way to go also. All right, everybody wrote it down? So then what they're asking about is the radius and interval of convergence, which means you have to do the ratio test. So to find the interval and radius of convergence, we need to do the ratio test. It literally makes no difference which one we do. Like it'll work out the same, either mine or his. Do we care? Ooh, maybe we should take a vote. All right. In the chat, do you want to do the one on the left or do you want to do the one on the right? Left or right? It's like Twix. You have to choose a side. Left, left. K equals 1, left, left. Okay, sorry, Ben. You're outvoted. But literally, guys, it will work. It's the exact same method. He'll just have a k plus 2 and I'll have a k plus 1. It'll be fine. So remember, the ratio test is the limit as k goes to infinity of a sub k plus 1 over a sub k. And we need this to be less than 1 because this is our r in order to get it to converge. Okay? So that is the limit as k goes to infinity. And here's the only thing that would have been different between the two of us. So the absolute value means you can ignore the -1 parts, because either one, when you take the absolute value of -1 is 1 and it's done. So you just kind of ignore that. And so then you take x to the 2 times k plus 1 minus 1 over k plus 1 squared. And you divide it by x to the 2k minus 1 over k squared. See what I did? K plus 1 goes in, k goes in. Now for Ben's, if anybody wanted to do Ben's, it'd be x to the 2 times k plus 1 plus 1, and then k plus 1 plus 1 squared. So you'd end up with k plus 2 over there instead of k plus 1. Right? Basically what's going to happen is these guys will be a little bit higher, and then this will be k plus 1. Okay? All right, so this piece right here is where a lot of people mess up. They forget that it's the algebra again. They'll just do like 2k plus 1 and they won't write it with parentheses, and then they'll get it wrong, right? So algebra rears its ugly head. So it's the limit as k goes to infinity. Algebra is like a set of rules and you have to follow them. So it's x to the 2k plus 2 minus 1, so that's plus 1, over k plus 1 squared. times it by k squared over x to the 2k minus 1, like that. Okay, so the k's can come out. They're not actually part of this, or excuse me, they're not actually part of the absolute value piece. They're part of the limit, right, but they're not part of the absolute value portion, right? So it's the limit as k goes to infinity, because k and k plus 1 are always positive, so they don't need to be part of the absolute value. What the absolute value is needed for is for the x pieces. And then if I take these two, 2k plus 1 minus a 2k minus 1, oh, all right, basic algebra. All right, hold on. Remember that a to the b over a to the c is a to the b minus c, yeah? So you do 2k plus 1, I'm going to write it. 2k plus 1 minus 2k minus 1, like that. And I know what you're thinking. You're thinking, well, it's algebra. I know how to do that. We write notes for ourselves because we will struggle with the algebra. All right, so then this is, oh, wrong pen. This is, well, we know what this is. This is 1, right? X or k squared, k plus 1 squared. That's the Hopital rule cheat, right? Because this is a polynomial over a polynomial. So this is 1. Like, we don't have to do it. But if we do that, then we take it out. We don't leave it inside the limit, which is where some of you are struggling on your homework. If you're going to do that limit, you're basically breaking it up into 2 limits. You're taking the limit of that one and the limit of this one. So this limit is 1. I take it out and I don't leave it inside the limit notation. Which a few of you did. And then this is the limit as k goes to infinity of x to the, okay, 2k plus 1 minus 2k minus 1. The 2k's are going to cancel. I'll be left with 1 minus a minus 1, which is 1 plus 1, which is 2. And now keep in mind, all of this all the way along has to be less than 1 in order to ensure convergence. I just usually stop writing it for a while and then I just bring it back at the end. So that's 1, that's out. That leaves me this part, right? There's no k left in this part. So I'm really just saying, hey, the absolute value of x squared is less than 1. Take the square root of both sides. The absolute value of x has to be less than 1. So my interval of convergence is from -1 to 1. However, I have to check endpoints. So this is sort of the interval. I just don't know if there's like a bracket somewhere or is there like a parenthesis somewhere. Like I got to check. So I have to check endpoints. I can tell you the radius of convergence right now. Think about what we're saying. Here, look at a number line. We're saying that x goes from -1 to +1, 0's in the middle. So your radius of convergence is 1. That part I can tell you right now. The radius is 1. We just don't know, am I doing like a bracket, like a closed dot, or am I doing open dot? Like what am I doing there? And to do that, I have to check the endpoints. So if I let x equals 1, x equal 1, then my series would be, let's go back, you got to go back all the way up to your OG series up here. You're going to put 1 in for that x right there. So it'll become -1 to the k plus 1 times 1 to the 2k minus 1. Nobody cares because it's 1. And then over k squared. This is just 1, right? 1 to any power is 1. So we don't really care about that. And so that means that I have an alternating, it doesn't even matter that it's alternating. That's convergent because that's a p series, right? So this is a convergent alternating p series. Which means I actually have to include 1. I now know that I have a closed dot on that side. And if I'm looking at my interval notation, I know I have a bracket over there on the right. I know I've got a -1 over here. I just don't know if it's a parentheses or if it's a bracket. Speaking of which, all right, let's check x equals -1. So I would have -1 to the k plus 1 times another -1 to the 2k minus 1 over k squared. Well, you just add the powers here. It's -1 to the 2k plus another k is 3k over k squared, because the ones will cancel because you're adding them. And again, that's an alternating p series. The alternating is irrelevant. It's a p series. P series are absolutely convergent. as long as the p is greater than 1, right? And it is, it's 2. So this is another convergent p series. Right? And therefore, I now know that my interval of convergence is right there. Right, my radius of convergence is 1. My interval of convergence is from -1 to 1. Good. That was 12A, right? I still probably didn't give you enough paper. I'm sorry. Like, I don't know what to do in 11.2. It's, to me, it feels like every single piece of a problem should take a whole page. It's just the way it is. Thank you, Shayna. Shayna thumbs up me. I appreciate it. Nice to know somebody's paying attention. All right, so write it down. Right. Good. Well, thank you. I see some more thumbs up thing. So I know you guys are ready. I gotta wait. Gotta get a few more. All right. That looked like the most people. Gaz, you're good? Okay, I saw him. All right, we're good. I was waiting. We're racing now. God, look at all that beautiful work. It just disappears. It's terrible. All right, so 12B. Okay, 12B. All right, so, whoop. Oh, I gotta throw this pen out. It's dying. I just pitched it. Okay, so let's see here. The series they give us is from k equals 0 to infinity of negative x over 10 to the 2k. Well, why bother with the negative? That doesn't even make any sense. Because that's this series. Here. Think about it for a second, right? Because 2k is always even. 2, 4, 6, 8, 10. So even if it was negative x, it would always be squared or to the 4th or to the 6th or to the 8th. So it's going to turn it positive. So because that's even, that'll turn that positive. And then I'm just squaring things. Negative x squared is x squared. 10 squared is 100. And then I leave the k power out there. Because why not? Now, let's think about this. We want to find the interval and radius of convergence. We have two options, which are, hold on, I'll go back. Oh, I've literally ripped it off because I use it so much. To find the interval and radius of convergence, your options are these ones, the ones that have an absolute value inequality in them. Yeah. So which one are you going to use on this one? Well, not me. There's the series. Which test? Yes, Emma. Very smart. Everybody see what Emma typed? See the K power in there? That's a root test. It's kind of an obvious root test, right? So like the root test will be pretty easy, in fact. It's not bad at all. So let's use root test. So we're going to use root test. Woo-hoo. I like it when we get to use the root test. We don't use it that often. I mean, we use ratio test, what, 80, 85% of the time. But we use root test every once in a while when it's just like super obvious. All right, so we want to take the limit as k goes to infinity. Oh, this is rho. As k goes to infinity of the kth root of the absolute value, which is irrelevant really because it's x squared, but whatever. I don't even need the absolute value in this case because x squared is always positive. So it doesn't really do anything. So, and I need this to be less than 1 in order to be convergent because I'm looking for the radius of convergence, not the radius of divergence. There's no such thing, right? So I want the radius of convergence. I want to know when those two graphs will overlap each other, right? So this would be the limit as k goes to infinity of the k and the k root disappear and it becomes x squared over 100. And there's no k anymore. I actually don't need this because the k got taken away by the kth root. There's literally no k in the problem, so there's no limit to find, right? So I just need the x squared to be less than, x squared over 100 be less than 1, so I need x squared to be less than 100. So I need x to be less than, less than 10, like that. Now technically it's squared, so it's like this. Because you learn in pre-calc, hell, you learn in algebra, that whenever you take the square root of both sides, you have to do the plus or minus, right? And so there's the minus and there's the plus. We all loved algebra class. It was all easy back then, right? It wasn't so bad. All right, so there's my interval of convergence right there. I can tell you the radius of convergence right now. The radius of convergence is 10, right? Because your interval of convergence is going from -10 here to 10 here. Obviously, 0 is in the middle. So my radius is right here. The radius of convergence is 10. Right? I just don't know if I get to include 10 and -10. I don't know if my interval of convergence has brackets or if they have parentheses or both. It's possible to have a bracket on one side and parentheses on the other. So I have to check. So let's check x equals -10. Okay, so again, don't go to the root test. That's not where you go. You go back up to the original series, right? Either one, it doesn't matter. But you're going to let x be -10 in here, right? So if I let x be -10, then my series is -10 squared over 100 all to the k. That would be 100 over 100 to the k, which is literally the series of 1 times 1 times 1 times 1 to itself, which is divergent, right? That's not going to 0. Remember the divergence test? Divergence test says that that sequence has to go to 0. There's no way that sequence goes to 0. That sequence is 1. 1 plus 1 plus 1 plus 1 plus 1 plus 1, right? You got 1. So you're adding up 1 infinitely many times, you're going to have infinity. And then if I check x equals 10, oh, hold on. I have an emergency. Give me 1 second. A friend's having to go to the hospital right this second because of his mom. Hold on. Okay. Sorry. So that's 1 to the k, which again is divergent. It's my neighbor. So he's letting me know he's rushing to the hospital. All right, so everybody good? Divergent, divergent. And that means that I can go back up now and say, okay, then that means my interval was this, right? That is the interval. It's from -10 to 10, right? Like that. Parentheses on both sides, because both ends were divergent. Good. Okay, so that was 12. I thought I saw something else floating in. We did 12, we did 18. Well, I guess we're good. That's 12 and 18. Cool. Cool, cool, cool. Anything else? So I noticed that you haven't asked me any questions on 11.3. Oop, hi, there's you, Jen. So 11.3, that's not a good sign. So 11.3, questions for me? Got another 15 minutes or so. Oop, hold on, there's a text message, but I can't see it. Yeah, everything. Yeah, Danielle. All right, come on. We gotta have, yeah, I'm just trying to think. Well, let me start you off with 1. So what'd you guys answer for number 1? Did you have an answer? I tried to tell you guys. I tried to tell you. Be prepared. 11.3 is brutal. 11.2 was no fun. I mean, that was pretty ugly stuff we were just doing there. All right, so 11.3. All right, so 11.3, number 1, what did you say? A, B, or C? Take a guess. I think I remember people asking about this last time. Let me pull this up. Can I erase this? Can everybody have this one? Yeah, you got it. All right, so hold on. I gotta erase. Okay. Okay, to remember, to have a Taylor series means you have to have a derivative, right, that exists, right? So you have to be able to do, Taylor series. You're gonna have to be able to have the 0th derivative, the 1st derivative, the 2nd derivative, and so on, right? So, is this a Taylor series? Synergy 0, so it's a Maclaurin series. Okay, so look at your 3 options. Which one cannot have f of 0? Because that's the one that can have a Maclaurin series or a Taylor series, right? Maclaurin's just a Taylor series that's standard at 0. Look at the 3 functions. Which one's no good? Yes, Jessica. Yep. That's it. So it's a little bit of a like concept question, right? So if you're going to have a Maclaurin series, which you are, because a Taylor series centered at 0 is a Maclaurin series. If you're going to have one, you need to have all these terms, right? So you need to be able to do f of 0. Well, I can do e to the 0. I can do sine of 0 plus 2, because sine of 0 plus 2 is sine of 2. But what I cannot do is 1 over 0 squared, because 1 over 0 squared doesn't exist. And that hasn't changed. Not even in Taylor series. So it's B, actually. Good. Right? And that might help you a little bit with the next one. Just recognize the next one, you're going to need to have functions at 1. Hint, 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 hint. So I'm not going to help you with number 1 or number 2, because number 2 is the same idea as number 1. All right, so then I saw, yes, Daniel, but you know, I didn't want to give away the story, Daniel. All right, so hold on, I'm looking for 11. 11. Which one's 11? Oh, 11A, 11B. Now you're not just picking the hardest ones, right, CJ? All right, hold on. 11B. All right, I don't know if I'll have time to do everything, but we'll see what we can do. All right, so if you're gonna have a Taylor series for, where's the heck? I've lost my, oh, there it is. I lost the other page of this thing. Yeah, of course, CJ, I'm teasing you. It's fine. Of course. That's what everybody needs reassurance on, right? Okay, if you're going to develop the stupid Taylor series, I mean, the wonderful Taylor series that you're going to run into later on in your calculus and engineering lives, so we're going to use the definition to find the first 4 non-zero terms of the Taylor series. We're going to write the power series using summation notation and determine the interval of convergence, which means you're going to have to do a ratio test just on the side as part of this much larger problem. Yep. All right. So this will be fun. All right, so we need to find the first 4 non-zero terms. And with sine, that's saying something, right? So if g of x is equal to the sine of 3x, right? And we want this at 0. So let's just start right off the bat. G of 0, oh crap, this was 11b, right? G of 0 is the sine of 0, and the sine of 0 is 0. Derivative. Derivative of sine is cosine. So it'll be 3 cosine of 3x, because of course I need chain rule. I'm gonna take a drink. Okay. G prime of 0 is 3 times the cosine of 0. 3 times the cosine of 0 is 3. Hold on, I'm texting my friend if he needs me to take his dogs so that he can be in the hospital a day. I'm the kind of person that when I see a car accident on the side of the road, I'm like, gee, I hope there wasn't a dog in there. because that's just how I am. Okay. All right. So, hey, first non-zero term. Yay, we got one. Woo! So we're going to skip that one. Second derivative. Second derivative, derivative of cosine is negative sine. So it's to be negative 9 cosine of, negative 9 cosine, negative 9 sine of 3x. Like that. Right? Because 3 times 3 is 9. You have to keep up with the chain rule. And then derivative of cosine is negative sine. Okay, well, that's going to be 0, right? D double prime of 0 is 0. So I don't care about that one. Next, third derivative. Derivative of negative sine is negative cosine. So it's negative 27 cosine of 3x. And so that one actually exists. The third derivative at 0 would be negative 27, which is negative 3 to the third, in case you want to know. So this is 3 to the 1. This is negative 3 to the third. I know I'm going to have to establish a pattern because I got to come up with a series for this thing anyway. All right, so there's that one. Next, fourth derivative. You might be thinking, well, I know it's going to be 0. Sure, but you still have to find it because you're going to have to find the fifth derivative. Fifth derivative, you're going to have to find the fourth derivative. So derivative of negative cosine is positive sine, and we're back where we started with. That's 81 sine of 3x. And then that's derivative of 0. Hopefully everybody learned the little parentheses notation. When you get up to high derivatives, we stop doing the prime thing, and we just say, you know, little parentheses 4. All right, fifth derivative. Derivative of sine is cosine. 81 times 3, I don't remember what that is anymore. 243? 243 cosine of 3x. So that would be the fourth or the fifth derivative at 0 is 243, which in case you're wondering is 3 to the fifth. It's almost like there's going to be a pattern. And then the sixth derivative is going to be 0, but I still have to find it. It's negative 729 sine of 3x, which is 0 because it's sine. And then last but not least, the seventh derivative is, and I just grab a calculator, negative 2187. Derivative of sine is cosine. So negative sine, so it's negative cosine. So the seventh derivative of 0, that was a 6 right there, is negative 2187, which would be negative 3 to the 7th. I have found the first 4 terms that are not 0. They're this one, this one, this one, and this one. Part A is done. You find the first 4 non-zero terms. Ta-da! Part B, or whatever. I might have done I, but you know, whatever. So I need to come up with a series for this. Well, it's a power series because those are the, oh, I take it back. Those aren't the terms. God bless America. The terms are the power series terms. Hold on. I was wrong. The first 4 terms are this. This is the answer to A. 3x minus 27. Oh, we got to put it in that series here. Hold on. Okay. Because you're putting it into the Taylor series, right? So, or the Maclaurin series, either way. So f of 0 was 0. F prime of 0 times x. That's 3 times x. Skip this one, right? Because the x squared term, here, look at it. Here. This would be the constant term. This would be the x term. This would be the x squared term, the x cubed term, the x to the 4th term, x to the 5th term, x to the 6th term, and x to the 7th term. Right? So for writing the series. So it's 3x minus, and then we need, well, it's plus negative 27 over 3 factorial times x cubed. So plus negative 27 over 3 factorial times x cubed. And then we keep going that way. So we would skip x to the 4th, and because x to the 4th turns into 0. Oops, sorry. And then we would have a plus 243 over 5 factorial times x to the 5. And then we'd skip x to the 6th because it doesn't matter. And then we have an x to the 7th, negative 2187 over 7 factorial times x to the 7th. Let's see if I'm right. I think I'm right. Yeah, I'm right. Okay, so we need some simplification help. So I take it back. I should not have circled that. I'm sorry. Here. I can't. I just can't. I shouldn't have circled those. I mean, they are the numbers I need, though, so I'm just going to leave them. This technically is the first 4 terms of the Maclaurin, or the Taylor series, Maclaurin series. However, I don't like it. I think it's kind of ugly. And I mean, I can make it work if I need to. Yeah, it'll work. It'll work. This is first term, second term, third term, fourth term. All right, I'll leave some space just in case. I don't think I do. I think I'm all right because I need this series, right? Isn't that part B? Part B is the series. So if this is part A right here, writing out the first 4 terms of the series, then I think that's what part A was. Now I'm curious. I lost it. Yep, that's what it was. Write out the first 4 non-zero terms of the series. So the coefficients are here, up here, but these are the terms of the series. So this is the answer to A right here. Okay. All right, then I need a series for this bad boy. So I'm going to need a whole bunch of pieces. I can tell it's x to the, and if I'm going to start at 0, because, why not? That's the way Maclaurin series start, right? Maclaurin series start at 0. That's how they roll. So I'll start at 0. I can tell it's x to the 1, 3, 5, 7. So I'm going to need 2k plus 1, right? Because it needs to be odd numbers. And I need to be able to put in 0 and get 1. So that's how I know it's not 2k minus 1. So it's 2k plus 1 to get me my odd numbers. Remember, I told you a long time ago, maybe at the start of chapter 10, that is a very common trick to know, right? How to get your odd numbers, right? Your odd numbers are 2k plus 1 or 2k minus 1 are the most common ways to do it. Technically, you can do 2k plus 3 and 2k plus 5 as well. But all right, so that's that piece. So I got the x, 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 x. Then I got 3 to the 3rd, 3 to the 5th, 3 to the 7th, right? So, and then it's doing the alternating thing, which I'll deal with. So I've got -1 to the k plus 1. Because it's alternating. Wait, there's a -1 to the k. It's -1 to the k because it's starting at a positive. So when I put 0 in, I've got to get a positive. And then it's doing 3 to the 1, 3, 5, 7, right? So it's the same thing as this. It's 2k plus 1, right? Because it's going 1, 3, 5, 7. And then my denominators are 1 factorial, 3 factorial, 5 factorial, 7 factorial. So it's 2k plus 1 factorial. There's your series. Ta-da! Hello, Maclaurin series. You can tell it's a Maclaurin series because it's just x. If it was a Taylor series, it'd be x minus something in parentheses. And then what do we need? Radius of convergence. Okay, that's a ratio test. So I don't know if I can fit it in here. I'm gonna have to grab another sheet of paper or another board. I have more boards if I need to. All right, so to do part C or part 3 or whatever, what do they want? The interval of convergence. So we're going to need to do a ratio test. So because there's a factorial, so it's kind of obvious. So we're going to take the limit as k goes to infinity of. Now I can drop the -1 thing because you don't need it because the absolute value makes the -1 part disappear. So that's irrelevant. All I care about is this. So it's 3 to the 2 times k plus 1 plus 1 over 2k plus, oh, mother, here, 2 times k plus 1 plus 1 factorial x to the 2 k plus 1 plus 1. All of that is just the first part of it. Remember, when you're doing the ratio test, it's the limit of a sub k plus 1 divided by a sub k. All of that I just did is just to get me to a sub k plus 1. This is all a sub k plus 1 right here. And then I'm going to flip and multiply, right? So I'm going to multiply by the reciprocal of this guy. So it's going to be 3 to the 2k plus 1, 2k plus 1 factorial. And then the x to the 2k was technically over 1. So it's going to flip and be in my denominator. like that. Now, where a lot of people make mistakes is they don't do the 2k plus 1 correctly. I know it kills me because they get to this point and then they literally don't do algebra 1 correctly. Like they will forget and write 2k plus 1 and make it 2k plus 2. This is 2k plus 3. Yeah, it's the algebra. I'm telling you, every time. It's always the algebra. All right, so literally, I'm not joking. The first conversation I ever had with my husband was literally about why do calculus students have such struggles with algebra? All right, so this is 2k plus 3 factorial. This is 3 to the 2k plus 2 plus 1, which is 2k plus 3. I'm going to put this x to the 2k plus 3 right here, times 2k plus 1. Yep, I am going to need another board. 3 to the 2k plus 1, x to the 2k plus 1. All right, so then, hold on. Canceling, lots of canceling. Okay, so, but I'm worried because I saw some of you guys cancel this wrong. So let me write this a different way. Give me 1 second, and then I'll show it to you guys. What I'm about to do, and I'll bring this up. You guys won't have to look at it like this anymore. I'm just going to rewrite it. 2k plus 3, 3 to the 2k plus 1. X to the 2k plus 3, x to the 2k plus 1. And then 2k plus 1 factorial, I want to write that out for a minute because this is where some of you guys were struggling. 2k plus 1 factorial is 2k plus 1 times 2k times 2k minus 1, dot, 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 dot. 2k plus 3 factorial is 2k plus 3 times 2k plus 2 times 2k plus 1 times 2k, and I'm running out of space, dot, dot, dot. Hold on, I'm getting there. And keep in mind, since this is a ratio test, I need the whole thing to be less than 1, but I don't have space for it. All right, so why did I do it that way? Well, because things are going to cancel. 3 to the 2k plus 3 or 3 to the 2k plus 1 is 3 to the 2. Same thing here. This is x to the 2, right? 2k plus 3, take away 2k plus 1, the 2k's cancel. You're left with 3 minus 1, which is 2. Over here, where a few of you messed up on your ratio tests in chapter 10, these are all gone. It subtracts 1 every time. You don't just jump to k. You jump to the next one down, then the next one down, then the next one down. And so that would mean it's got 1 over 2k plus 3 times 2k plus 2. Thankfully, I can write this large enough. And then I'm going to finally be like, yep, and that has to be less than 1. I mean, all of this is to r, right? And it has to be less than 1. Okay, 3 squared is 9. So that bad boy can come out, right? So, and then I'm left with this bit in here. But where is that going to, right? So this is 9, the limit as k goes to infinity of x squared over 2k plus 3 times 2k plus 2. What is that? Give you a minute. I've been writing fast, so. Yes, Jessica. Yeah. That's 0, right? That's x, whatever x is, divided by infinity squared. Does that, right? That sucker's going to 0, right? It's 0, 0, 0, 0, 0, right? It's x squared over infinity, right? So, and x is a variable, of course. So that is 0. Is 0 less than 1? When is 0 less than 1? Oh, wait. It's 9 times 0. You know what 9 times 0 is? 0. So when is 0 less than 1? Always. This is always true. Therefore, my interval of convergence is negative infinity to infinity. There's no endpoints to check because infinity doesn't have endpoints. Its radius, by the way, is infinity, right? So if you want to know the radius of convergence. There you go. My dog is looking at me and wagging her tail. A different dog, the other dog. I don't know what she wants. All right, so everybody good for interval of convergence, radius of convergence on that one? That was 11B. All right, let's see what else we got. Technically, we're done, but I can keep going for a while, and I can do 15 and 16. But if you got to go, I understand. I'll put up the recording for later. Everybody good? So be warned, you are taking a test on this on Monday. And as you can see, the chapter 11 questions are going to be rough, and they're going to be worth a lot of points. So you don't want to miss them because there's so many pieces to these. So I recommend. You guys all know where you can get extra practice from, right? Everybody knows about the study plan in my math lab. So if they know that 11.2 and 11.3 are a struggle, you can go to the study plan and grab extra questions of whatever you like. Yeah, I know. My husband's flagging me. Dad's like, what is this dog doing? We have no idea what this dog is doing. She's really eager and wagging her tail at me, and I have no idea why. So I still have 3 more problems to cover because it's 11.2 and 11.3 today. Anyway, sorry, talking to my husband. All right, so everybody good? So if you need more help, and I think you probably will, you can get more problems out of, and these aren't worth anything. They're not going to count against you. You can just practice in there. And of course, you have your My Math Lab due tonight anyway. So your My Math Lab is due this evening on 11.2 and 11.3. So you can work on those. And those worksheets are both due tonight. And then you can start working on your sample exam because that is due Monday. And will hopefully help you study for the exam. All right, if we're good there, I will work on 15, right? 15, which is a Maclaurin series. If I can find 15. 15. All right, going back to the screen. Okay, so we're going to give the Maclaurin series, or given the Maclaurin series, oops, we lost somebody, blah, 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 blah. Use the properties of the power series substitution factoring to find the first non-zero terms from the Maclaurin series. Give the interval of convergence for the new series. Okay, so they're telling us this is true. This actually isn't so bad. This one isn't so tough. These are the ones we like. If you're in 11.2 and 11.3, they're 11.3. These are the ones that are like, okay, we can do this. This isn't so bad. This isn't so terrible. Because they're telling you that the square root of 1 minus 4x, oh, sorry, this is number 15, is equal to, what was it? 1 plus negative, oh, rats, hold on. I forgot to write what they were giving me. 1 plus x equals 1 plus x over 2 minus x squared over 8 plus x cubed or 16 plus blah, 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 blah. Okay? And then they're talking, it's for this, right? So technically the absolute value of x is less than 1 or equal to 1, because anyway. Okay, so then what we're going to do is we're going to plug in negative 4x. So wherever there's an x, because when you look at how these things are changed, see how x turns into negative 4x, see it? So what's going to happen is instead of x over 2, you're going to put negative 4x over 2. Instead of minus x squared over 8, you're going to put in negative 4x squared over 8. And then plus 16 cubed negative 4x. It goes like that. Like I was saying, these are actually ones that are not bad because there's just substitution. So we substitute and we get 1 minus 4 over 2 is 2x. 4 squared is 16. 16 divided by 8 is 2. So minus 2x squared. 16, well, it's 4 to the third over 16, which is 4 squared. So that's going to be minus 4. Minus 4x cubed. So, sorry, that was a minus. It's plus negative, so it's minus. So it's actually going to keep subtracting from that point on. It's 1 minus 2x squared minus 4x cubed minus blah, 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 blah. Okay, and that's all they wanted, right? They just want the first 4 terms of the Maclaurin series. Ta-da! First 4 terms of the Maclaurin series are done. Did it. I love these ones because they are literally like you substitute into the one they gave you. That's it. Okay. And then we will need the interval of convergence, right? Because it does say give the interval of convergence. So we know it should have been, okay, this is the ones that do change. So for this original series, it was absolute value of x because that was just plain x. But for our new series, the interval of convergence, I can spell. That's a conv. Forget it. I give up. I'll just start again. All right, interval. There we go. It's my own fault for being too lazy to write the word convergence out. Okay. So it was absolute value of x, and now it's going to be, wait for it, negative 4x. Because you substituted everywhere, including into the interval of convergence. Yeah? So that means that negative 1 is less than absolute value, so that's just going to turn into 4x, which is less than 1. So that means that negative 1/4 is less than x, which is less than 1. Okay, that's the interval. Oh, 1/4. Geez Louise. I passed my 2-hour mark. What can I tell you? All right, so that's 1/4. Now, you'd love to like be done, but you're not. You've got to check your endpoints because one of those might have a bracket. Okay, so we need to check endpoints. Check endpoints. You never can avoid it. Then all of 11.2 and 11.3, you just always have to check endpoints. Okay, so you take your endpoints, which would be x equals negative 1/4, and you plug it into the series. Now you're thinking, well, I don't really have the original series. Yeah, but you don't need it. You'll see what happens. So when I put in negative 1/4 for x here, I'll have 1 minus 2 times a negative 1/4 minus 2 times a negative 1/4 squared minus 4 times negative 1/4 cubed minus blah, 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 blah. Okay, so that's 1 plus a half minus 2 over 4, so that's minus a half, right? And then 4 over, let's see, that's minus. Yeah, I think I'm going crazy. Yeah, this is right, minus, and that's minus. This will be plus right here. So this is plus 4 over 4 cubed, so that's 1 over 4 squared. So that's 1 over 4 squared like that. I feel like I did one wrong. Oh, I did. It's 4 squared, not 2 squared. Oh, my Lord. It's 16. Jeez, this is 8. Sorry, that's 8. 1 minus 2. Yeah, I feel like I'm going crazy. 1 plus a half minus an eighth plus 1 over 16, right? Yeah, we're good. So let's think about this for just a second. This is equal to, if I think of it from k equals, I don't freaking know, 1 to the, because this is 16, right? So 1 to the infinity. Isn't it really like 1 over k, or excuse me, 2 to the k? Oh, if I start at 0, there it will be. Because 2 to the 0 is 1, 2 to the 1 is 2, 2 to the, 2 to the 3, and 2 to the 4. I skipped 2 to the 2. Interesting. But something like that, right? It's convergent. Why is it convergent? It's an alternating 1 plus a half minus an eighth plus a 16th. It's a convergent series. Maybe I wrote it wrong. So 2 to the third, 2 to the fourth is 16. Yeah, that's right. But there's no 2 to the third term or 2 to the second term. Maybe I shouldn't have broken it down. Maybe I should have left it as 2 over, because this was 2 over 2 squared, 2 over 2 squared, so 2 over 2 to the fourth. Maybe I should have left it like that. Anyway, it's a convergent series. Just trust me. It's what do you call it? Geometric. It's one of the geometric. I think I have to play with this a little bit more. I think I have to write it like this, and this one's 2 over 16, right? And then this one's 2 squared over 2 to the 2 to the 3. So that's 2 to the 6, like that. And if you write it like that, you can make the pattern something to that effect. So either way, it's convergent. And then when you put in 1/4, it's not. When you put in 1/4, it's divergent. So it's 1 minus 2 times a fourth minus 2 times a fourth squared minus 4 times a fourth cubed. And it doesn't have the alternating piece, so it ends up just heading towards negative infinity, as I recall. So that one's divergent. I'd have to play with it, but it has to do with this one's alternating, so it like survives the alternating series test, as I recall, and this one does not. And so then that means that our interval of convergence is negative 1/4 with a bracket and positive 1/4 with a parentheses. Oh, that looks like a ninth. I'm too tired. 1/4 like that. So parentheses over here, bracket over here. Maybe I should have just gone further. But they only wanted us to do 4 terms. So, but if you play with them enough, you'll find out that the one that alternates converges, and the one that just subtracts, it's subtracting too much and it diverges. So, ta-da! There you have it. All right, so that's 15, right? And then what was the other one? 16 and 19. Okay, so 16. Oh, 16 actually is really easy. 16 requires no work. Oh, it requires a little bit of work, but 16 does not need the full half page even. All right, so I like that. That's good. So, all right, everybody got it written down? You wrote? And then I don't even know about 19. Oh, 19 is not bad either. I'll show you 19. So 16 and 19 are the only 2 left. All right, so Taylor series. It's good times. All right, I saw people thumbs upping me, so I'm good. I'm going. All right, 16. 16, oh, let's see, how do I put this? Okay, so they give you 1/1 plus. The thing about 16 is you have to notice something. Oh, sorry, they gave it to you as this, but that is that, right? They're one and the same. And that is equal to 1 minus 2x plus 3x squared minus 4x cubed plus da 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 da. And then it's for the absolute value of x is less than 1. Okay. Okay, so, and they didn't even want if you'll notice, they didn't even ask for the interval of convergence on this one. We like that. When there's no interval of convergence, I know endpoints to check. It's lovely. All right, so the trick is that they're giving you this problem, which is 1 over x squared minus 4x plus 5 squared. So I need to turn this thing into that thing, and I'll be done. Yeah, it's not as hard as you might think. So for starters, I'm just going to break off the 5 into a 1 and 4. So I'm going to make it 1 plus x squared minus 4x plus 4 squared. I can do that, right? It's 4 plus 1 makes 5. And so then I need to factor this bad boy right here. You'll notice I'm not even using summation notation because I don't need it. Right? There's nothing here. So this guy right here is x minus 2 squared. So this is equal to 1 over 1 minus x minus 2 squared squared. What am I going to do with that? Well, I'm going to take the series and I'm going to plug that in. Ta-da! Oh, it's plus. It's not a minus. Sorry. It was a plus. It was right there. Plus. Sorry. So I take my series and I substitute x minus 2 squared into it. So wherever you see an x, what was x now becomes x minus 2 squared. And it stays. So my series would be equal to, right, this little lovely guy would be equal to 1 minus 2 times x minus 2 plus 3, I need all the space I can get. Hold on. Plus, x minus 2 squared, my bad, x minus 2 squared. Plus 3 times x minus 2 squared to squared. So it'll be x minus 2 to the 4th, right? Because squared is to the 4th. Minus 4 times, it'll be x minus 2 squared to the 3rd, which is x minus 2 to the 6th, right? Because 2 times 3 is 6. Plus, and you're done. That's it. Algebra. Right? You had to use algebra to change the problem they gave you into the form that they gave you, right? So if you want to make it match this one, you got to change it to the form that matches this one. And that's it. Now, technically, they didn't ask for it, but if you want an interval of convergence, you would need, instead of x, you need x minus 2 squared to be less than 1. I don't really need this bit, right? Which means x minus 2 is less than 1, which means negative 1 is less than x minus 2, which is less than 1, which means negative 3 is less than x, which is less than 1. So that would be the interval of convergence. They didn't ask for it, but they could have. Technically, I should check endpoints, but I don't really have the series. So, I mean, I can go fiddle with it. So it's going to be diverging in both of them, because when you put negative 3 into this, you're getting negative 5 to the squared, negative 5 to the, it's diverging. So if you check your endpoints, you'll diverge both times. Question for me? I hear a microphone.
Aren't you adding 2 though? Why would you get negative 3 for that?
Negative 3 for what? You're not, wait, which one? Oh, you're so, oh, sorry. You know what? You're so right. I went the other way. You're right. It's this way. I went the other way like an idiot. Thank you, Maribel. I was just whipping through it because I was just doing it on the fly. I hadn't done it. It's 1 to 3. Sorry. It's still going to diverge. I can see it from here because those coefficients are not going to get any better. So when you put in 1 or you put in negative 1, or excuse me, put in 1, put in 3. If you put in 3, it becomes 1, 1, 1. So it's just the numbers themselves and they don't converge, right? It's divergent for both of them. So when you put in x equals 3, it diverges. You can see what's left. It's like 1 minus 2 plus 3 minus 4. That diverges. And then when you put in x equals 1, it becomes, let's see, 1 minus 2 plus 3 times, plus 3 minus 4. It's the same way both ways. It diverges. So this is your interval of convergence. I should have added that in, but I didn't. I'll make a note of it for future to add it. I'm writing it down right now. There we go. So hopefully you are too. X equals 3, 1 minus 2 plus 3 minus 4 diverges. There we go. And they didn't ask, but your radius of convergence is 1. This is kind of an interesting one. This is more interesting than ones we've seen before. So if you look at your radius of convergence, if you graphed your number line, you're going from 1 to 3, not negative 1 to negative 3. I'm an idiot. So technically 2 is in the middle. So the radius of convergence is 1, right? So in other words, it's 2 wide, and the radius is from the center out. So the radius of convergence is 1. Again, they didn't ask it, but I'd write it down for your own benefit because that might help you, right? Figure out what you're doing. And sorry, I messed up my math. You're adding 2 to all 3 of those pieces. So it's 1 and 3. All right, so that's 16. Everybody good for 16? No, good. And then I thought the last one that somebody asked about was 19. That makes sense. But 19 won't be too bad. I think we just have to write out the Taylor series. The younger dog has come back. The one that keeps shifting around underneath my desk. All right, hold on. Let me lift up my cord. All right, there you go. Go ahead. Go under the desk. There you go. Yeah. The big dog keeps putting herself under the desk, the one that's 65 pounds. Okay, if we're good, I'm ready to erase. Oh, sorry about that. Good. Waiting. I saw one thumbs up, but I'm waiting for the rest. Everybody good? Then we'll do 19. If I can find 19. Oh, I saw some thumbs up. Yep. All right. So compute the coefficients of the Taylor series. Okay. About a equals 4 for g of x equals 1 over the square root of x. About with a equals 4 about the given point, a equals 4. I don't know why I said that both times. That doesn't make any sense. I think that's a typo. Okay, so use the first 4 terms of the series to approximate 1 over the square root of 3. Okay, so, and again, I think that's a typo. We've got typos today. I could just say about the given point a equals 4, and you don't need both of them. Okay, so then, let's see here. We got to find those. So, right? Okay, so think about a Taylor series, since you're trying to approximate a Taylor series. Taylor series is going to require you to find, in this case, g of a, g prime of a times x minus a, g double prime of a, right, g triple prime. So when they say find the first 4 terms, they're saying find these pieces, right, because those are the first 4 terms. So basically, you just need all your derivatives and your substitutions. So g of x is that. G of 4, because that's the value they give you, because a is equal to 4, would be 1 over the square root of 4, which is 1/2. Okay, then g prime of x would be negative 1/2 x to the negative 3/2, which is the same thing as negative 1 over 2. I don't know if I care about this. Yeah, I'll just write it this way. Square root of x cubed, like that. So then I need to find g prime of 4. And again, you could use Desmos if you want. I mean, you're just trying to get 4 plugged in here. Square root of 4 is 2. 2 to the third is 8. 8 times 2 is 16. So this is negative 1 over 16. And again, you can use Desmos if you so desire. All right, you have calculators. And then g double prime of x would be, bring the 3/2 down. So 3/2 times a half makes 3/4. X to the negative 5/2. Okay, and then g double prime of 4 would mean I'm putting 4 into this. So if I rewrite this, it's 4 square root of x to the 5th, like that. Square root of 4 is 2. 2 to the 5th is 32. 32 times 4 is, oh, actually, I don't know, 128. I was going to say 64, and that was wrong. It's 128. So it's 3 over 128, like that. And then the third derivative, these aren't the terms, by the way. These are just the coefficients. I'm just getting all I'm doing is I'm taking the time to find the derivative so I can find this piece, and this piece. I'm just finding those coefficient terms. That's it. That's all I'm doing right now. So, and then this one is, well, let's see, 5/2 times 3/4 would be negative 15 over 8 x to the negative 7/2. Which would be negative 15 over 8 square root of x to the 7th, like that. I'm only doing that to help myself because I'm trying to be able to do this in my head, although I can't. So this will be negative 15 over square root of 4 is 2. 2 to the 7th is what, 128. 128 times 8 is 1024. There you go. All right, so then the first 4 terms. So now I'm ready to substitute. So I'm going to go and just plug in right here. So I start with f of a, which was 1/2. Oh, shoot. Let me just say. So g of x, which is, what was it? G of, I'm just trying to think. G of x is equal to, roughly, 1/2 plus, oh, minus, because it's a negative, right? Minus 1 over 16, 1 over 16, oh, you can't see it, times x minus 4, because a was 4 for us, plus, all right, f double prime, or in my case, g double prime, which is 3 over 128 divided by 2 factorial. So that'd be 3 over 128 times 2 factorial times x minus 4 squared plus, God bless America, minus, sorry, I forgot about the alternating part, minus 15 over 1024 times 3 factorial x minus 4 cubed. And you're done. They actually don't want you to keep going, right? They say the first 4 terms, so there they are, the first 4 terms. Now, the actual Taylor series has infinite terms, right? So it's just a question of how many terms do you want to get the decimal places of accuracy that you're looking for. So they said to use the first 4 terms, and then they want you to use this to find g of 1 over the square root of 3. So what are you going to do? Well, you're going to plug 3, because 3 is your x. You're going to take 3 and plug it in wherever there's a x in that formula. Use Desmos. Right? You plug that thing into Desmos, and then you stick 3 into it, and you're done. And you'll get some decimals. Cool for that one? Questions, troubles? So actually, it's not so bad. The worst ones are actually earlier. The ones where you have to like derive it and find the derivative and all that jazz, that's a lot of work. 18 and 19 and 17 and 16, they're not too terrible. They really aren't, because they're like tricks. Like take the Taylor series, and like fiddle with it until you get this new series, right? The ones that suck are the ones that take 2 pages to do, like 12 and 11, right? 11A and 11B. Those are a lot of work, right? 11A, 11B. Those are the ones that they're going to be not pleasant. But in a way, these aren't pleasant either, not because they have like a page and a half of work, but more like because you have to fiddle with it. You have to be good at that algebra and that manipulation, and in this case, derivatives. And you have to do all those derivatives correctly. And this is why you have to have Desmos on this test, because I have to have you be able to do this, right? So, good. Other questions before your exam? Anything for the good of the order?
Where do you find the sample exam at?
It's in your course pack. It's, oh, help me out, guys. I don't know where it is in there. It should be white. It should be with the worksheets, maybe at the very end of it.
Quite possibly.
Do you have your course pack in front of you? Because I put them in there so that you don't have to print them or anything. They should be right in there.
Yeah, I found it.
Help. Okay, you found it? Good. Yeah.
They're
They're all.
Thanks.
No worries. Other questions? Anything? Well, we stayed longer today, but it was important. This stuff is not easy. It's okay. Don't beat yourself up and be like, I'm bad. It's not because you're bad. It's just, this is just tough stuff. This is not easy. And the only way you get better at it, honestly, is practice. You practice. That's how you get better at it. So I would love to tell you as a Calc 2 student that I was awesome at these, but I've gotten better at them with practice. Right? And that's just the nature of the beast. Okay, well, we're done with 11.2 and 11.3. You guys still have, sounds like a lot of homework you still have to do to turn in for tonight, because you're my math lab and your worksheets are due. So get those done, and then I'll see you on Monday for your exam, and I'll start the exam about an hour early like usual. I'll start around 9 a.m., get everything prepped over the weekend so that you're ready to show me your screen and all that good stuff. Okay? All right, I'll hang around for questions. Let me pause the recording here. I'm actually going to resume recording real quick. So let me just say this again so everybody can hear it. The phenomenal thing about power series and why they're so useful is that we can take a discrete thing that has a series, a discrete sum, and it approximates and actually is that curve for the interval of convergence, in this case from -1 to 1. The more terms I include in that series, because currently I'm only including 3, that's why there's this huge gap here. But if I change it to 7, 8, there's a tiny, tiny gap. And if I let it go to infinity, they will be completely on top of each other from this line until this line. And those 2 lines, that's the interval of convergence from -1 to 1. And then the endpoints at 1 and -1 always have to get checked, because sometimes they're in there, sometimes they're not. Every problem's different. Every problem's got, so you always got to check those ones. That's why we're constantly checking the endpoints, because the endpoints of the interval of convergence are strange. And the power for this is that you're able to take a discrete thing that uses algebra and approximate a function, which could involve calculus. And that means that our calculus can get broken down into discrete packets. And that's how computers often deal with them. That's how engineering often has to deal with them, because we don't want the actual function. We want a decimal approximation that's close enough to get us what we need to do. Like I was saying, to get the man on the moon. I watched a little Apollo, because it's Apollo 11 went up 51 years ago today. So I watched a little Apollo 11 documentary last night. So now I'm thinking of all the engineering involved in that. There's a lot of engineering in getting those guys up. And so this is one of the Taylor series is definitely one of the things that they use to do the engineering, for sure. No question about it. You kind of have to. I mean, when you get into upper level engineering. Cool. All right, let me pause.